Okay, so we're going to be looking at the Doppler effect and particularly some practice examples. All right, so hopefully you all can see my page. Can I just quickly ask, can you give me a thumbs up if you can see the page just that I can know? You should be able to see questions. Brilliant. Okay, thank you. So, ladies and gentlemen, over here we have a question that came from a past paper. You'll notice that the Doppler effect isn't always worth the hugest number of marks, but it is quite a, I guess it's an easy section if you use the marks well. However, sometimes the questions get very tricky. Sorry, I was suddenly looking at this graph and thinking I'd picked one that was on the next section, which is the photoelectric effect, because you suddenly got things about Hertz and, it got confusing. All right, no, this is still Doppler effect. So we're looking at one of the questions. Please, before anybody asks, because I know you're going to be on my case in just a second, I think most of these are from the 2013 to 2015 range of questions. I tend to look further back rather than the ones you're most likely to have done if you do the most recent papers. What I've tried to do tonight is to hand pick ones that involve simultaneous equations and just a little bit of extra complexity. I'm hoping that you're up for the challenge. Please remember, as always, if you're not up for the challenge, you can give it a go and then you'll get the solution at the end, but at least you've tried to work through it. So the question here says the graph below shows the relationship between the apparent frequency of the sound heard by a stationary listener and the velocity of the source traveling towards the listener. All right, so you're firstly asked to state the Doppler effect in words. Now, ladies and gentlemen, I know all of you should know the Doppler effect. What I'm going to ask you to do right now on any piece of paper that you got near you, you're going to need pieces of paper. So tonight, if you don't have a pen, a calculator, and a piece of paper, quickly run and get one. I would like you all, please, to write out the Doppler effect for me in words. The reason they say in words is if not, you could write down that formula at the top, and that would be your definition. So please, can everybody quickly write it down, and then we'll check in just a second. All right, if you're done, can I ask you to quickly give me a thumbs up? When it comes to this stage, as we head into, I guess what we'd call the final preparation stage for your exams, I know many of you don't think you're yet in the final preparation stages, but you are. It is so important that every definition you're asked to do, that you actually write it out. I know it's tempting to go, oh, I know that. You know it until you're asked it, and then you got a problem. So here we go. The Doppler effect is the apparent change in frequency of a wave due to the relative motion of a source and an observer. Keywords: apparent change in frequency and relative motion, source, observer. If you've kind of left off a word, so you say apparent change in frequency and you leave off of a wave, we'll probably still give you the mark. All right. Now this question here says use the information in the graph to obtain the speed of sound in air. Remember, in this equation, I don't like this one, so I'm going to cross it out here. Okay, but remember that the speed of sound in air is they're now asking us to work out the value of V. Okay, so I know this is a rather tricky question to lump you straight in with. I'm going to give you a second just to read through it, read through the information, and then give your best attempt. All right, please don't panic if you can't do it. We will go back and we'll go over it. Okay, so I'm going to quickly erase everything and I'll carry on working it out now. You do, well, you're not going to erase everything. You try and work out how you'd get the speed of sound in air from the graph. I'm going to give you one big hint because this is probably the bit where most of you are going to go wrong. On here, we can see the frequency of the listener, which is that value, and we can see V of the source, which is that value. We know that it's a stationary listener, so this bit disappears. My question to you is, how do we get the frequency of the source? Can anybody tell me what the frequency of this source is? I'll give you a hint, it's definitely from the graph. Anyone brave? Anyone sure enough of themselves, or is everybody lost? Okay. Yay, Nasia's right. It is 800. The reason is if we have a stationary source and a stationary observer, so a velocity of 0 over there, we will get the true frequency. So that is how we know over here that the frequency of the source, the actual frequency of the sound source or whatever the source this is 800 hertz. Can I quickly ask, before we go any further, who would have said the same answer? I'm just curious to see who'd have seen the 800 hertz and who would have been lost for the rest of the question. I think most of you would probably be lost for the rest of the question. So well done if you saw that. Now that I've given you the heads up, you should be able to pick any point on this line. Pick a nice point so that it's easy to see all the values, and you should have everything you need to plug into that equation to work out the value of V. Please do so right now. Okay, go for it. It's a bit tricky here reading the graph. Do your very best. Just so you know if your answer is right, the speed of sound through, in this case, air, should be between about 300 and 350. If it's near 330, that's a good sign. All right, if you think you've got an answer, please give me a thumbs up. Good. Brilliant. Okay, I don't know if anyone needs a little bit longer. You may end up with slightly different answers to me if you chose slightly different points, but they shouldn't be like completely different. Okay, so I'm going to share now so that we can go over this. Let's just see. Okay, just quickly replying to a question. Rebecca, the Fs being 800 is the true frequency of the source. And the true frequency of the source will be the frequency where there is no relative motion between the source and the observer, or both the source and the observer are stationary. So in order for the source to be stationary, its velocity must be 0. If you look on my graph, I've circled the velocity of the source being 0, and where the source has a velocity of 0, the frequency that's observed is 800. It's a clever use of graphs to make a question considerably more complicated. All right, I hope that that makes sense. So I'd like to go over my solution with everybody quickly. What I did was I took this equation, first of all. I knew that the velocity of the listener was 0 because it was a stationary listener, so I left that off. You remember on Tuesday, I went through how do you decide if it's a plus or a minus? And since they told us that the source was traveling towards the listener, I knew that I wanted the frequency to be bigger. So this value here must be smaller, which is why I put in the negative. Please, as always, if you want to memorize that instead, go for it. But I find that I've got limited brain capacity to think about memorizing things, so I work it out each time. Then I went and picked a point on my graph. I picked that point there because it looked like where it crossed very neatly. I don't know, you can't see now because I've doubled over it, but over there's a very neat point. Where I went from that very neat point is I went across to here. This is a horrible graph to work on, but there's 900, I think somewhere here is 850, and I counted there are 10 spaces between them. So we are one block less, one block represents 5 units, so it's 895. Then I went here, I dropped my vertical, and I counted that there were actually 5 units back from 40, which made this 35. And we knew that our true frequency, the frequency of the source, was 800 hertz. From there, the maths gets a bit tricky, but I said 895 divided by 800 gave me that value. And I took this and then multiplied it up to there, which is why it's now on that side of the equal sign. Then what I did was I multiplied these two out and I got those two values and I got my V. Then I took this V that way and this constant the other way. Then I subtracted them. Then I divided this by that. I'm saying this and that because they're big numbers. And I got a velocity of 329,74 meters per second. Since it's so close to 330 and it's in the right range, I'm pretty sure that short of a silly mistake, it is correct. Can I quickly have a show of hands? Did any of you get the same answer as me? Anyone? Yay, well done. Okay, so this question I think was a little bit of a nasty one because if you didn't pick up how the values worked, it got very tricky. Okay. All right, so if you got a different answer and you got a different answer, because you had exactly the same things as me, but you rounded en route. So say, for example, if you said 1,12 here, and then you multiplied it out. So if you rounded en route here, you may have ended up with a different answer, but the only way that you'd have got full marks for this is if it was because you rounded there. I strongly recommend against rounding. I think it changes the value. If we had engineers who rounded, we'd have houses that had doors that didn't fit, and we probably still do, but things wouldn't fit together because if you round all of your values while calculating, things aren't going to sit flush against each other. So please avoid rounding if you're good at using a calculator, and if you have the time, as I do over here, to write out the answers. All right. Yes, yes. Sorry, I think that your answer here, if it's much smaller than 325, I'm going to say it's very wrong. And if it's bigger than 335, it's very wrong. So even if I went and took a value here of 1.12, and I times it by 35. And oh my goodness, what do I do here? That then gets divided by 0.12, even if I rounded on root everything. So if I took this value up to 1,12, which is the only acceptable rounding you're allowed to do here. Obviously, I guess if you picked a slightly different point, we'll discuss that just now, I ended up with 326,67. So that's how big a difference I could get from rounding. Now, what some of you may have done that's a bad idea is that you picked points that weren't on the graph. So if you picked this silly point over here, obviously your answer would be very different to mine. But if you picked any of the other points, it shouldn't be so significantly different. If you read the scale incorrectly there or there, then obviously your answer would change as well. But sadly, the kind of change that actually means it's wrong. It's not change and still be right. Okay. So somebody said they used, okay, so you've got it. I wouldn't use any of the points that they used. I actually used a point that just lay on the best fit line because it looked really nice and neat. And somebody said they used 937. Let's me quickly go and see. There's 900. 900 takes me to there, and 37. Okay, so maybe if you did 937, let's just quickly say what they got as the answer. So they got 333. So as I said, anything between about 325 and 335, I would say would probably be fair in getting it right. But if you're asking about questions that are kind of in the 400s or anywhere bigger than out of that range, it's probably not just due to a small error. It's that you did something big that was wrong. And unfortunately, that's very, very wrong. All right. So you're then asked to sketch a graph of apparent frequency versus velocity for the sound of the source if the source was moving away from the listener, and it is not necessary to include any numerical values. So this is a little bit of a tricky one. We haven't done it. In fact, I must be honest, I don't think I've ever thought about doing it before. So we're going to quickly do this. I'm going to give you a chance to try and see what you would get as well. Remember, it's a sketch and you don't need any values. Well, you can put on one relatively easily, but you only need to put on one. Okay, go for it. Try and think about what you'd get if you were to follow some logic there. I would say that there's one value that I do expect you to put on. Okay, remember in the graph that we've already given you, as the velocity increases, the frequency will increase as well. Please, this is velocity that's increasing, not distance. If you remember from the graph that we did on Monday, if we're comparing distance to frequency, it's a fixed value and then it changes to a different fixed value. All right. Can I quickly get a show of hands? Who's already got that done? Quick sketch. It's a graph line and then a shape. Just the two. Okay, well done. Okay, fantastic. All right. So I'm going to share. Mine looks like that. So basically, the important things for you to get your marks here, they didn't really say anything about no numerical values. Okay, so I would say here, I don't know where they're giving the second mark, which is a little bit tricky. I would personally have insisted on having the 800 as a starting point. So if the velocity is 0, I would say that frequency being in hertz and this being in meters per second would be crucial. There is a small chance that they give you a mark for the axes, but I can't imagine. So what I would give a mark for is that it's a straight line with a decreasing gradient. If it's only 2 here and they specifically didn't tell you to put in the 800, I would say that my mark here is straight line 1 mark. So if you've got a straight line in any orientation, you get a mark bonus. And then the second one would be that it's got to be decreasing. So as the source speeds up, the frequency will decrease. But remember, because they're moving away, the apparent frequency is lower than the true frequency. All right, Can I quickly just see who got the same answer as me or a similar graph? Whose graph looked sort of the same? Okay, well done. Those of you that aren't getting these right, please don't panic. The point is that if you got them wrong tonight, next time you do them, you'll get them right. Okay, so I'm just quickly checking that everybody's taken a screenshot of everything that they need with regards to this question, because I'd like to move on to the next one. Okay, all right, so I'm going to clear all of my drawings. I'm going to hope that as I scroll down, it doesn't make a big mess. Oh, that was very good. Okay. I would say here, and I actually thought about that, so I'm just going to quickly go and answer the question. They said, does the gradient have any special meaning? Now, we usually would say that here, I think the gradient, I just got to actually think about what it was. It was this value and this value. I don't think it necessarily has a specific reading because we're not looking at a change in y over change in x or a change in x. It gets messy. So there might be one, but it's not one that I've ever thought about. This plus and minus in the middle messes it up just a little bit too much, I think. So it's not like with a whole bunch of the other rules where we can create graphs that typically the gradient has a meaning. Here, I'd say that it's just that there is this change that happens. I could be wrong though. Okay, I'm speaking a little bit out of my depth with that one. Okay, so here's our next question. Once again, I'm going to scribble all over this because I don't want you to look at it. Actually, before I do that, do any of your schools use the other version, the Afrikaans one? I assume it's Afrikaans, one that has a B somewhere in it. Okay, cool. Then nobody will mind too much. Please, if it is one that you do use, you're welcome to unscribble it, but I'm pretty sure you're used to using either. All right, so question 6.1 says a sound source is moving at a constant velocity past a stationary observer. The frequency detected as the source approaches the observer is 2,600 hertz, and the frequency detected as the source moves away from the observer is 1,750. So I'm going to deal with a situation where I draw a picture. This is my observer. As the source approaches, here's my source, as it approaches, the frequency observed is 2,600 hertz as it's approaching, and as it moves away, the frequency drops to 1,750 hertz. Now, I've got to give you one of the biggest heads ups with regards to this. These are the observed frequency. The frequency of the source is not the average of these two. I know it's very tempting, and there's a part of you that goes, surely it goes the same amount up and the same amount down. It doesn't work that way, okay? So you may not average them to get the true frequency. We have not yet been told anything about the true frequency, and I'm telling you one thing right now, that it is not the average of the two. So please don't assume that. You are then told that you can take the speed of sound, that's your V value, as 340 meters per second. So we're going to work through a couple of the questions which go rather quickly. Also, this is assisting me a little bit with what I call polyfillering. It's where when we do a lesson in a hurry, you've sometimes got sections you haven't covered. And then when you get these questions, you get a chance to go, oh, I didn't mention that. Let's quickly fill in that little gap. All right. So question 6.1.1. Name the phenomenon that describes the apparent change in frequency detected by the observer. Anybody? What is the answer? You do all know this.
Doppler effect.
Thank you. And I'd even give it it is the Doppler effect. All right. Your next question is to state one practical application of the phenomenon in the field of medicine. Anyone? We use it in the field of medicine. I'm sure at least one of you, I didn't cover this in the last lesson, I know it, but at least one of you should have done this at school. Does anyone else? Someone's typing. Okay, to detect blood flow or blood flow rate, that is correct. So you could use it to detect, so blood flow meter, okay. I mentioned in the last lesson that I've actually had one of these. They're not fun. So you could use it as a blood flow meter. You can also use it to detect a fetal heartbeat. And it gets slightly complicated because it uses a combination of ultrasound. Now, be careful here. Okay, Sam, you've got to be careful. There is a difference between Doppler effect and ultrasound. So when we're detecting the fetal heartbeat, we use ultrasonic to send in a wave and it bounces back. But I know that I've had quite a large number of discussions about exactly what aspects of it is because it's Doppler and what aspects is actually ultrasound. So ultrasound sends in a wave that you can't, it's beyond the range of audible hearing, sends in a wave and the wave bounces back off something and comes back. But depending on how fast this thing is moving, it'll change the frequency as it bounces back. So just be a little bit careful about saying ultrasound is the only thing. I would say maybe uses ultrasound to detect fetal heartbeat. Just make sure that you're covering yourself a little bit more than saying ultrasound on its own. Okay. Now we come to the very tricky question. How do we know it's very tricky? Because it's worth 6 marks. And that is to calculate the speed of the source. So we are looking for Vs. Now, I'm warning you right now, this question is nasty. The other thing that I'm warning you about is that you are going to work it out using simultaneous equations. So you are going to use this equation. You're going to bear in mind that the source is traveling at the same speed coming in and going out. It doesn't slow down, it doesn't change direction, it doesn't do anything. So your value of Vs will be the same for both equations, okay? Also, you were told the value of V, which you know here. You know for a fact, where are we? You know the frequency observed, so you know that. So effectively, you are going to be doing a simultaneous equation with 2 unknowns. You don't know the frequency of the source, and you don't know the velocity of the source. Once you've got your 2 equations, I don't mind how you do the simultaneous equation, you are going to solve for Vs. All right. Now, I warned you right at the beginning, not an easy question. Can I quickly just get a show of hands? Who feels confident that they can at least sub it in and get 2 equations? Okay, good. That's a good start. And then from there, what I want you, after you've got the 2 equations to do, is you're going to do a simultaneous equation. Now, to make this fair, I'm going to work out what the 2 equations are. You're welcome to continue beyond there, but before I continue the whole way through my answer, I am going to tell you what the 2 equations are so we don't waste a huge amount of time. Good news is once you've got to the 2 equations on their own, you have got all but the last mark. Okay, so you effectively, if you equate them properly, you've got probably everything but the last 2 marks, and when you equate them, everything but the last mark. So you only lose 1 mark if you're not good at the end part with maths. All right, so I'm going to pause this and I'm going to plug things in to work out what the equations are. You please do the same. Okay, can I please ask when you've got the 2 equations that you just quickly give me a thumbs up? Okay. What makes this one so tricky is you've also got to decide whether it's a plus or minus in the formula. You've got to think. All right, I think that's about long enough before I give you the formulas. So I'm just quickly going to explain this as I do it. If you have already got your answers and you're happy with them, you can quickly mute me while I continue here. So what I did was I started when they're moving towards, and the frequency was 2,600. The speed of the wave through the medium or air was 340, so I put it in there and there. Then I had to realize that this was towards, so the frequency had to be larger, so my denominator had to be smaller, so that was a minus. Then I put in VS and FS. I must be honest, okay, I probably should have started, I'd lose a mark here, that FL is equal to V over V plus or minus VS FS. So I should have written this in, I assumed it was there. Okay, I've got mine written over here, so I didn't write it out. So there's 1 mark for your formula. Here, because of how everything was laid out, you would probably, of the 6 marks, get 1, 2, 3, 4, maybe. Okay, I'm probably being a bit over generous there. Probably 1 mark for both of those. Okay, so there's quite a large amount of marks, making sure that that's a minus because it's larger, and that's a plus because it's small and it's moving away. Now what you've got to do, please, is you've got to get your simultaneous equations together. Can I have a show of hands? Who got that bit right? Oi, okay, sure. More of you did, it's okay. There was just a delayed response. Okay, ladies and gentlemen, please do your simultaneous equation. Good luck. Sorry, that's an equals. A part of it disappeared. There we go. I'll make it look like an equals at the top again. Okay, my answer seems exceptionally big. Can I please ask if you have got an answer that you quickly posted on the chat, just that I can compare it? It's like 440 kilometers an hour. Seems quite fast. Oh, don't worry, I've already picked up my first mistake. Yeah. Okay, good. You've all got the right answer. I've just picked up that I suddenly changed 2,600 to 3,600. That is very special. Okay, I'm going to quickly go and change that. Okay, we'll compare in just a second as soon as I've gone and corrected my own typo. I get a different answer still. We're all getting slightly different answers. Okay, I'm going to go back and double check that I haven't missed any little. Oh, I am useless tonight. Sorry, I've just seen that I copied across. This is getting ridiculous. I copied across 2,600 is 3,600 and 1,750 became 1,700. I do not know what I am doing with regards to silly moves. Okay, 2 seconds longer. The good news is since you're all getting different answers, I'm going to keep working as well so that I can be sure that mine is actually the right one. Yay! Okay, and I got the answer that most of you got. Whew, that took a little bit of not messing up multiple times. All right, ladies and gentlemen, I'm pretty certain at this stage that I've got the right answer because most of you have got the same. So let's quickly run through it. Your answer was 66,44 meters per second. So the first big important step that you had to do, for me at least, was I multiplied this up to the top and divided that down to the bottom. And that made it nice and easy for me to quickly get Fs on its own. I immediately then equated the two Fs values. Now, the nice thing is I didn't need to show that. I just went straight in. So I said this times this divided by this. There it is. This times this divided by this. There it is. And then I said I'm canceling the 340 on both sides. I then multiplied this out, which became a lot trickier because this 2,600 became 3,600. And this, where was the other one? 1,750 became 1,700. I don't know what I was thinking, but I promise you, you all do the same thing occasionally. Then I multiplied that out, got my values. All constants went to one side. All of the terms containing VS went to the other side. I divided my value by this value, and I got my answer. All right, ladies and gentlemen, can I quickly have a show of hands? Who got that one correct? First time correct, I should probably say. You are brilliant. Okay, well done. That's a lot of you. Okay, I'm sure that the rest of you made many silly mistakes like me. So hopefully you understand this. Now, I just quickly want to show you one thing. And the reason I want to show you this is I want to prove to you that the frequency of the source is neither of these. So to work out the frequency of the source, I can plug this value back in here. So if I do 1750, it's 340 over 340 plus 66,44 multiplied by the frequency of the source. Okay, so if I quickly work this out, 1750 times by brackets 340 plus 66.44 divided by 340, I get that the frequency of the source is 2091,97. That wasn't asked, but it's important for us to consider it. If you did the average of these two, 2,600 plus 1,750, and you divided it by 2, the average would have been 2,175 hertz. Can you see that although the true frequency lies between these two, it does not lie in the middle? So please, that is a very important thing to do. Probably about 3 years ago, they suddenly started doing these simultaneous equations. And everybody got very confused because up until that point, they'd only ever done plugging things in. You are almost inevitably going to get one of your questions in the exam is going to be a simultaneous equation, tricky one, and you need to be ready for it. If you've got two unknowns and they're the same values, you're going to have to solve using simultaneous equations. All right, well done, everybody. Now what I'd like to do, I think I can safely clear everything from here for us to answer. So I'm just going to quickly clear everything. The question then says, will the observed frequency increase, decrease, or remain the same if the velocity of the source is increased as it moves towards the observer and as it moves away from the observer? I'm going to give you just a second to quickly think about those two answers and write down something for each of them. The previous question we did, hopefully previous as in before this version of question 6, will hopefully get you on the right track to answering it properly. Okay, I'm assuming we can jump straight in. If it moves towards the observer, the frequency will increase. If it moves away from the observer and the source velocity, so if the velocity increases moving away, it would decrease. All right. And please note if it remained at the same constant speed of source, then there'd be no change. But here, because there's a change in velocity, there will be a change in the observed frequency. All right. In the last lesson, we looked a little bit at spectral lines. Now, I must confess, I had a large number of the boys in my class come to me the next day and say, ma'am, you lost us when you went down that thing and you started speaking about lines and stripes and stuff. So please, as I said when we did it, if you didn't understand the lines and stripes and stuff, don't panic. It's not too important. You can probably get away with answering questions like this still. So the spectral lines of star X at an observatory are observed to be redshifted. Now, I do need you to know this bit. I do need you to know that on the spectrum, blue has a high frequency and red has a low frequency. Once you've done the section on photoelectric effect, this makes way more sense because we spend quite a lot of time looking at the color spectrum and also looking, as I mentioned, that ultraviolet is above there and infrared is below here, and this is our visible spectrum. So where it says explain the term redshifted in terms of wavelengths, okay? Redshifted, now I did everything here in terms of frequency. This is a high frequency and a low frequency. Since V is equal to F lambda and V is constant, our rule is if you've got a high frequency, you've got a low wavelength. So high frequency here, we've got a low wavelength. Low frequency, we must remember that it's a high wavelength. If we are red shifted, we shift towards the red. So therefore, I would say the red shifted in terms of wavelength, I would say that the apparent wavelength is higher than the true wavelength. All right, so that would kind of be where I'm talking about in terms of red shifted. Because this is for 2 marks, I do feel that there's an inclination that I should also say because the frequency of red light is lower. That's kind of my safety blanket, just in case there aren't 2 marks for that first statement. All right. Next part of the question here says, will the frequency of light observed from the star increase, decrease, or remain the same? Well, we've already established if it's red shifted that it's gone to a lower frequency. So in that case, it will decrease. The bit that they didn't ask us here is whether it means that the star is moving towards us or away from us. And I want to ask everybody here, what does it tell us? Is the star moving towards us or away from us? Anyone?
Ma'am?
Yep.
Ma'am, please can you re-explain? I'm completely lost at this section of ultralight and visible light and everything.
Were you at the lesson on Tuesday?
Yes, ma'am.
Okay, cool. So do you remember I did that very complicated bit where I spoke about the fact that you get the full color spectrum and then the electrons transition from one place to another, blah, blah, blah. Do you remember all of that?
Yes, ma'am.
Okay, this links on to all of that. This bit about knowing your spectrum, is this what's confusing you here?
Yes, ma'am. How come the frequency is going up if it's shifting to the left and the wavelength is going down?
Okay.
It's
Don't panic, don't panic. All right, so I'm just quickly, everybody's got the answers here. I'm just going to quickly answer my last question, then I'm going to come back to it. Since we were told here that it is red shifted and it's going to a lower frequency, we can quickly say here that the star moves away. All right, so what I'm going to do very quickly now is, I know I keep deviating across to this, but I think it's doing what's necessary where it's necessary. Is that I'm going to quickly do a little crash course for you on electromagnetic waves. All right, magnetic waves, good. Now, the last time that many of you did electromagnetic waves, unless you've done photoelectric waves this year, is when you were in grade 10. And what you hopefully learned when you were in grade 10 is that an electromagnetic wave is created when you've got a moving charge. So you've got a little electron or a charge that moves up and down. And as that charge moves up and down, it creates a changing electric field. But whenever we have a changing electric field, that changing electric field causes a changing magnetic field at 90 degrees to it. And electromagnetic waves are able to travel through a vacuum purely because the one changes the other. I do this weird thing where I go, well, now I've got to get it right. I can't even do it now. Okay, but you got one changing, then the other changes, then one changes, then the other change, and they continuously induce each other to happen. Okay, so it's a little bit like a feud between two families that began so long ago that nobody knows what caused it, but it just keeps going because the one creates the other, which creates the next, which creates the next. Okay, now our electromagnetic waves has a full spectrum of different kinds. At the one extreme, and I like them in this order, so it can be done opposite way around. At the highest energy, which is also the highest frequency, we have a type of electromagnetic wave called gamma. Gamma radiation. That's the symbol for gamma. Just below, so this, remember, is a spectrum. This is a full line going from one extreme to another. Okay, so we got the highest possible one is gamma. Just below gamma, we have X-rays, like X-rays that you use to take X-rays of your body. Below that, we have UV, like ultraviolet rays that you use for sun tanning. Okay, sometimes you use them as party lights or detective banknotes are real. Below that, we've got visible. Visible light is the light that we can see. Still below visible, we have infrared. Below infrared, we have microwaves, and below microwaves, we have radio waves. This is the order in which they get arranged according from highest frequency to lowest frequency. So over here, I'm going to say we've got the lowest energy and the lowest frequency. All right. Now, there was an equation that you learned also in grade 10, and you're going to learn it again this year if you haven't already, which says V is equal to F lambda, where V is equal to the velocity or speed of the wave, wave speed. That's how fast the wave travels, and that is measured in meters per second. F is our frequency. That's the number of waves per second measured in hertz. And lambda, L-A-M-D-A, is our wavelength measured in meters. Okay, now something that you may remember from grade 10, or maybe you don't, is that all electromagnetic waves travel at the same speed. It's called the speed of light, and it's 3 times 10 to the 8. In fact, meters per second. In fact, the speed of light is so special that it often gets the symbol C. So sometimes instead of saying V is equal to F lambda, people say C is equal to F lambda. But the point here is because all of these waves have the same speed, if something has a high frequency, then its wavelength must be low so that those two can multiply together to give you the same speed. So if we've got a high energy and a high frequency, gamma rays have got an exceptionally low wavelength. If we go to radio waves have the lowest possible energy and the lowest frequency, but they have the highest wavelength. In fact, when we say highest wavelength, most radio waves are from a meter into the kilometers. Okay, so that's how big their wavelength is. Remember, a wavelength is the distance it takes for your particles to complete one full wave. Okay, back to waves. All right, does this make a little bit more sense? So all of
Yes,
this
ma'am.
comes back to old theory that you're supposed to know. Within this range, what we've also got to remember is that visible light comes in a full color spectrum. It's going to have ultraviolet is just beyond the upper scope of what we can see, but it'll be purple over here. And then just below the purple, we'll have blues. Okay, so we'll do the rainbow color here. And then just below that, we'll have our turquoisey colors. And then we'll have our green. And then we'll have our yellow. And I'd better make this a little bit longer. It's not going to fit in. And then we'll have our orange. And then we'll have our red. Okay, so that is your full electromagnetic spectrum. When we say that something is red shifted, it means that its spectral lines on the full continuum of colors will be shifted towards the red end. The red end over here is going to be the low frequency and the high wavelength side. So anything that's red shifted will have a lower frequency and a higher or a longer wavelength. Anything that is blue shifted, don't ask me why it's blue and not purple. Anything that is blue shifted will have a higher frequency because it's on the high frequency side and a lower wavelength. Okay, so if the spectrum of lines that we should get should be here, here, and here, but instead we find them here, here, and here, it tells me that everything is shifted closer towards the red side compared to, and I'm going to put purple here even though we call it blue, compared to the blue side. Okay, so if we see our spectral lines on either our absorption or emission spectrum from a star, that tells us that the frequencies are lower than expected. So there is a lower apparent frequency, and that lower apparent frequency tells us in terms of the Doppler effect that the planet and, well, whatever that thing is we're seeing and ourselves must be moving away from each other. Because if there's relative motion apart, then according to the Doppler effect, the frequency drops. Frequency drops when we're heading towards red. Okay, so this tells us that they're moving apart. If it heads towards the blue, which I didn't write in here, it means that they're moving closer. So if we were to observe blue shifting in a star, we'd see that that star was moving towards us. All right, does this make good sense to you? Okay, I don't know.
Yes, ma'am.
Thumbs up. All right, so I'm now going to quickly stop sharing that. Okay, so ladies and gentlemen, I think we've got just a few minutes left, and I don't think we're going to get through a whole new question. Can I quickly ask, just by show of hands, who found that the examples we did tonight helped them to understand what it is that they needed to understand on this section? All right, fantastic. So I was kind of giving you a little bit more practice. I think the simultaneous equations are tricky, but they also give you preparation for what you're likely to get asked in an actual exam. All right, so thank you very much, ladies and gentlemen. Please, as always, make sure that you get onto Siavula and you go and practice. At this point, you can still get into the Momentum Masterclass. So there's still a Momentum Masterclass and a Doppler Masterclass, that Doppler effect masterclass that have spaces in them. So please, can I recommend you go and practice there? I know that the end of the year is coming a lot faster than we thought it was. All right.